We'll look at different key contributors in earth pressure research. So far, we have covered the William-Rankine method using the lower bound approach. William-Rankine is a very famous geotechnical engineer, and he has made a lot of contribution to the Geotechnical Society. The annual Rankine lecture organized by the British Geotechnical Society is named after him. He studied the state of stress at a point at failure in a semi-infinite questionnaire medium and related the principal stresses at failure in 1857. This is the lower bound approach in estimating the lateral earth pressure. The lateral earth pressure calculation in terms of stress ratio that involve a cohesion term is usually attributed to Rankine. This may not be strictly correct. In fact, Rankine only disregarded cohesion, but also advocated that it should not be considered at all, arguing that cohesion is a temporary condition, liable to destruction by atmospheric effects. However, it is not exactly so, but this has shown how incredible insight he is. Rankine earth pressure theory is only applicable to very simple problems like the smooth vertical wall. For more complex geometries and problems where wall friction is significant, the solutions are not easily found. Thus, the Rankine earth pressure theory is in practice rather restricted in its usage. In fact, a more general method was proposed even earlier in time. In 1700s, there was a French military engineer who was tasked to design the defense bombardment. His name is Charles Coulomb. He has conducted a lot of retaining wall research. Coulomb has proposed a method to evaluate the limiting of pressure in a soil mass at failure. He observed that the failure in a soil mass tend to occur along well-defined failure planes. However, he had two problems to solve. The first problem was defining the failure criterion along these slip planes. In other words, what contributes to the resistance along these slip planes and how can these factors be accounted for mathematically? The second problem related to the geometry of the failure wedges. Before we go details on Coulomb method, let's look at his bibliography. Charles Coulomb, born in 14 June 1736. He graduated from École d'Eugénie in 1761. He joined Corps of Engineers of the French Army with a rank of lieutenant. He was then posted to Martinique in the Caribbean to bolster its defense by building new fortifications at Fort Bourbon. These fortifications consisted of massive gravity retaining walls with moat and obstacle in front. His famous research work on shear strength of soil and limit equivalent method of retaining wall design were conducted between 1764 to 1772. The limit equivalent method of retaining wall design used the upper bound approach. Coulomb's works on geostatics was written in his highly acclaimed essay and was presented to the Académie des Sciences in Paris in 1773. The objective in Coulomb's work was to determine as far as a combination of mathematics and physics will permit the influence of friction and cohesion in some problems of statics. With this one single article, Coulomb recreated the science of friction. This slide shows the friction that happened between the two surfaces. The friction angle is the angle measured between the normal force W and the resultant force R, which is attained when failure occurs in response to the shear force H. We will now look at the Coulomb methods in more detail. Coulomb's friction law. Coulomb had learned from his experiment that the shear resistance of rock consists essentially of two components, The first derived from the cementation and bonding within the rock structure and is termed cohesion. The second derives from the friction that exists between blocks of the rock structure. The stresses acting on the slip plane are resolved into a normal component sigma n and a shear component tau. At the point of failure, tau f is resisted by two components of resistance. The two components are a constant cohesive component denoted by C, a frictional component that is proportional to the normal stress sigma f. And therefore the shear strength of the material is the summation of both components, where the shear strength tau f is equal to C plus sigma f times the tangent phi, in which phi is the angle of friction and tangent phi is the coefficient of friction, commonly denoted by mu. And this gives rise to the Moe-Coulomb failure criterion. When Coulomb was conducting his research on the retaining wall, he observed that for sandy soil, most of the failure surfaces were almost planar. For this reason, he assumed that the failure surfaces are planes. However, Coulomb's approach can, in principle, be applied to any class of failure surface. The failure of the planar surface can be described using the Moe-Coulomb failure criterion, where the failure envelope is expressed as tau f equal to C plus sigma f times the tangent phi. With the known failure mechanism, which is a failure wedge that he has observed in his lab, and also the failure criterion, the Coulomb can now develop his earth pressure theory. Let us see how Coulomb deals with the active state. This is an example of how to derive the Ka for the cohesionless soil, smooth and vertical wall condition where there is no friction between the wall and the soil and the ground is level. First, we need to choose a failure wedge with any value of h and theta. And within this failure wedge, there's a few force acting. Then we look at the forces here. We have Q, which is the active force, W, which is the weight of the soil mass within this failure wedge, and then F, we have the shear force, or what we call the resisting forces, and the N, which is a normal force. So the N is actually the summation of W cos theta and the Q sin theta, while the frictional force is W sin theta minus Q cos theta. And then you can simply calculate the weight of the wedge using the equation here, W equal to half of times the gamma prime times the h power 2 cotangent theta. We know that along the slip plane, the limiting friction must be reached so that the frictional force over the normal force is equal to the tangent phi prime. After we rearrange, and we will find out that the Q, which is the active force, is equal to W times the tangent theta minus phi prime. We have arbitrarily assumed that the slip plane is inclined at an angle theta to the horizontal. However, there are many potential slip planes inclined at all angles, but only one will lead to the failure of the soil mass. This is the critical slip plane, which is also the slip plane which gives the highest value of Q. To evaluate this value of a critical angle, we equate the first derivative of Q to 0. And finally, it will give the theta C equal to 45 degrees plus phi over 2. And we substitute this theta C into the Q, and then you will get Q equal to half times the gamma prime times h power 2 times tangent power 2 in bracket pi over 4 minus phi over 2. Previously, we have obtained the Q, which is the total force on the back of the wall, or in other words, the active force, and it is not the earth pressure distribution. So to find the earth pressure distribution, we note that there is an equally likely slip plane occurring at a depth of h plus delta h and inclined at the same critical value of delta c. By considering the delta h and the corresponding delta q, we now have the total horizontal active pressure sigma ha prime, which is equal to gamma prime times h times the tangent power 2 pi over 4 minus phi over 2. This slide shows that the tangent power 2 pi over 4 minus phi over 2 is actually equal to 1 minus psi phi over 1 plus psi phi. Therefore, the sigma ha prime, which is the active horizontal pressure, is actually equal to the Ka times the sigma v prime. Hence, the Coulomb's earth pressure theory with the prescribed failure wedge give the same solution for active earth pressure as the Rankine earth pressure theory. And now we come to the passive state and how to derive the Kp value using the Coulomb methods. In passive state, the wall is actually being pushed towards the soil itself, so that the failure wedge is actually moving outwards. The frictional force is now moving downwards, so it is opposite to what we have seen in the previous example. And the N, normal force, is now W cos theta plus Q sin theta, and the frictional force is Q cos theta minus W sin theta. Similarly, along the slip planes, the limiting friction must be reached so that the FON is equal to tangent phi prime. So that now we have this Q cos theta minus W sin theta over W cos theta plus Q sin theta is equal to the tangent phi prime. And now we have the Q equal to W times tangent theta plus phi prime. After we obtain the lateral force, we need to differentiate it to get the critical slip angle, and it shows that the critical slip angle is equal to 45 degree minus phi over 2, and minus the sign of a minus here because it is different from the active state where the theta is equal to 45 degree plus the phi over 2 for the active state. And now we have the theta equal to 45 degree minus phi over 2. We substitute it to this Q, and then we will get Q equal to half times gamma prime times h power 2 tangent power 2 pi over 4 plus phi over 2. And eventually we will get the horizontal passive pressure equal to the Kp times the sigma v prime. So once again, for the passive case, the Rankine's and Coulomb's earth pressure calculations return the same solution. After looking at the example 1 and 2, we have the Ka and Kp derivation. Here are the summary. The Coulomb method is based on the assumption of a failure wedge, which means that the failure mechanism has been established. It is very important that some form of optimization be undertaken as part of Coulomb's method, at least within the choice of slip surface, such as finding the critical value of theta. This should be considered as an integral part of Coulomb's calculations. We can think of Coulomb's calculation loosely as an upper bound. It will tend to give an optimistic or unsafe solution, since we are obtaining our solution from a scenario that already involves a failure mechanism. Interestingly, we know that with the smooth wall assumption, Coulomb's earth pressure theory with the prescribed failure wedge gives the same solution for active and passive earth pressure as the Rankine's earth pressure theory. Recall that the Rankine's earth theory gives a lower bound to the correct failure load. In other words, Rankine's earth pressure theory generally gives what can be considered as a safe or pessimistic solution. Since Rankine's method gives a pessimistic or safe solution, lower bound, Whereas the Coulomb method gives an optimistic or unsafe solution upper bound, the fact that both solutions are identical implies that in this special case, Rankine's and Coulomb's calculation produce the correct solutions. And this is only valid when the problem is simple, such as the wall is vertical and smooth, and the ground is level, as in this case. Coulomb methods and Rankine method produce the same critical angle for the passive state and the active state. This is not something unexpected because the Rankine method uses the stress field, which is a triaxial. This is the stress field used in the Rankine methods, where the theta f is calculated to be 45 degree plus a phi prime over 2, which is similar to the Coulomb methods for the active state. We'll see how the Coulomb method is applied to the non-vertical rough wall and the sloping ground surface. The material used here is still the same, which is a cohesiveness soil with phi prime parameter. For this problem, we have additional parameters such as the slope backfill, angle, beta. We have a delta for the friction between the wall and the soil, and we have alpha measured from the ground level to the slope face of the retaining wall. And the forces acting on the failure wedge is quite similar, except that the end now become the R, okay, inclined at the angle of phi prime. This table summarizes the forces acting on the failure wedge. So we have 4 forces acting on the failure wedge, which is W, width of the soil, R, which is the resultant of the normal force and the force due to the shear strength component, the FC, which is the friction along the failure subplane, and the Q, which is the active force. For each forces, we can see the magnitude and the direction, whether they are known or unknown, depend on the type of forces. So basically, the directions are all known for all the forces, but for the magnitude, the known forces is W and FC, the unknown forces, which is R and Q. So the Coulomb used this force polygon to solve the problem. However, it looks quite complicated. The solution for this force polygon is rational, but is quite cumbersome, and then it has to be repeated for different trial failure surfaces. A simpler and more efficient method has been developed by Koeman. Koeman used the graphical method to solve Coulomb wedge problem, and his solution is much faster compared to the Coulomb force polygon method. This topic is not going to be tested in the assessment, so I will leave it to you to have a look on how to use this graphical method. If you have any problem, you can just contact me. I will try to explain to you. Now, note that the Koeman method is a graphical approach to solve the forces acting on the Coulomb wedge, hence it is still based on the Coulomb method. Koeman method is quite versatile in that it can solve for different problem geometry, like the sloping backfill, sloping back face of wall, and also consider wall friction. For regular wedge or block geometry, analytical solution can be derived, and I will show you in the next 2 slides. The analytical solution for the non-vertical rough wall and sloping ground surface is given in this slide. The Q, which is the active force acting on the wall, is given as Ke times gamma prime h power 2 over 2, where the Ke requires the input of alpha V prime, delta, and beta. And note that the Q does not act horizontally. So if you want to find the horizontal component of Q, which is QH, then it can be calculated as KAH times gamma prime H power 2 over 2, where the KAH is equal to Ka times sine alpha plus delta. For the passive case, we have the Q, which is the passive force acting on the wall, is now calculated as Kp times gamma prime times H power 2 over 2. And the Kp has a similar expression, except that the sign plus and minus used in this equation can be different, so you have to be careful when you use this expression here. Then other than that, the QH and KPH is quite similar, except that the lateral pressure coefficient, which is a K, is now become KPH or KP. Coulomb method can solve for non-vertical rough wall and also the problem with a slope backfill. However, the solutions are approximate and the accuracy is much depend on the assumed linear failure plane, whether it matches the actual failure surface. How do realistic failure surface look like? Is it planar, curved, or it's a combination of both? Now we are going to look at the realistic failure surfaces, and these failure surfaces are actually depends on the direction of the wall movement and the soil movement. We will look at 4 possible cases in both. First, we look at the active condition, where the wall moves away from a soil mass. The soil will move down relative to wall, so that in this case the reaction of the force PA due to the lateral pressure of the soil is inclined outwards, with the friction of the wall and the soil is positive. If we compare the failure mass, okay, assumed by the Coulomb or Rankine method, where the friction angle, where the angle, critical angle is 45 degree plus 3 over 2, and then it is smaller than the realistic failure surface. Okay, and if you look at the passive condition, so we know that in the passive condition the wall moves towards the soil mass, but in this case the soil moves out relative to wall, so the reaction of the wall will be inclined downwards. And if you compare the critical angle of the slip plane, the first assumed by the Rankine or Coulomb, which is the red dashed line, you can see that the soil mass within this area is much more smaller compared to the realistic failure surface. The third case that we are going to see here is at the active condition, where the wall moves away from soil mass. However, this time the soil moves up relative to wall. So when the soil moves up, then we will have the reaction which is inclined downwards. Okay, so that the friction will be negative, and you can see that the failure plane is more like a planar, similar to what we assumed, even though this is slightly smaller in terms of the soil area mass, in terms of area mass. If you look at the passive condition, where wall moves towards soil mass, then in this case we have a soil moves down relative to wall, and then the reaction is positive, or what we call it inclined outwards. And if you compare the failure surface, so it is more like a planar surface, similar to what we have assumed for the Coulomb methods. The assumption in Coulomb methods, where the failure plane is a flat surface or the plane surface, is not too bad for the active conditions, but for the passive condition, it may overestimate the passive pressure, and especially when the wall is rough. So now we look at how to obtain the Ke and Kb for the more realistic non-planar failure surfaces. In 1900s, Kakut and Caricel has developed methods to estimate the lateral earth pressure, assume non-planar failure surface. Kakut and Caricel produced tables of earth pressure based on non-planar failure surfaces. They assume the logarithmic spiral to represent the rupture surface. This improvement is very important for the passive earth pressure where there is a soil wall friction. However, for the active pressure coefficient, the result obtained using these logarithmic spiral ruptures provides negligible difference to those obtained using a planar surface, which are by the Rankine and Coulomb method. Eurocode 7 and XC provide charts based on the Kakut and Caricel works. Here are some charts based on the Kakut and Caricel works. For these figures, we can obtain the Ka for the beta equal to 0 and alpha equal to 90 degree case, which is for the vertical wall and with a horizontal retained surface. This is for Kp condition. This is to find the Ka for sloping backfill, and in this case the delta, which is the roughness of the wall, is equal to 0. This is also for the Ka condition, but in this case the delta is equal to phi prime, meaning that the wall is very rough. Kakut and Caricel actually come up with analytical solutions based on the log spiral failure surface, both for the cohesionless soil and cohesive soil. And in this slide you can see that there are two equations. One is for smooth wall, the other one is for rough wall, and the equations are very complex and it is not easy to use. That's why the Kakut and Caricel come up with the graph or tables, as we seen earlier. These are the analytical solutions for cohesive soil. This is the summary. So we have covered the Rankine methods in 1800s and Coulomb methods in 1700s, and the last one, Kakut and Caricel method, which adopt the log spiral failure surface assumptions during the 1900s. Here are some historical perspectives, so you can have a look. Rankine assumed that the limit equivalent state would be reached by the slightest deformation of the soil. However, we have learned that the limit equivalent for the active state can be achieved by the slightest deformation of the soil, but not for the passive state. To mobilize the passive earth pressure fully, we require the wall or the soil to move in a large magnitude. There are many earth pressure theories developed by different researchers over the years. However, the Coulomb methods and the Rankine methods remain the most common used method to predict the lateral earth pressure.